Introduction to trigonometric functions. Let's start out by thinking about a practical problem. Say you want to buy a ladder and you go to a store where they have two kinds of ladders. One is 12 foot long and another is 8 foot long. The store clerk explains that when you place this on the wall, the angle that you can have with the ground has to be 70 degrees or less. And he explains that it's dangerous to make the angle larger than 70 degrees. Naturally, your question would be, how high can it reach when you place it on the wall? So you're trying to figure out the distance between this point to that point. So you're trying to figure out this length. Also for the same for the 8 feet thing. For this ladder, you want to figure out this length. Okay, one way to figure these lengths out will be, of course, to take the ladders out and place it on the wall and measure the lengths. Now, this is possible, but it's not that convenient, and you wish that there was a mathematical way to figure this out without really having to take the ladder out and place it on the wall. And the answer is that there is such a way. Now, the mathematical way to approach this question is to use similar triangles. If you think about this angle of the triangle that you see here as a 90-degree angle, and this one also 90 degrees, then you can think about a smaller triangle, which you can draw on a piece of paper, which has angle 70 degrees here, and a right angle here. So there you have a right triangle. Now, because these angles are the same, we know from geometry that these three triangles are similar. So if I denote this height by x, this height by y, and this length by a and then b, then because of similar triangles, we can say what x is to 12 is what b is the height here, right? And x is also the height. So what b is to a. You can say the same thing over here. You can say what y is to 8 is what b is to a. Now, once you have these similarity equations, then you can solve for x and y to figure this out. So, if I multiply 12 both sides to the first equation, then the 12 cancels out, and you end up with x equal to 12 times b over a. Same thing here. You multiply 8 both sides, 8 cancels, and you get y equals to 8 times b over a. Now, this ratio b over a can be actually measured on your piece of paper you drew by using a ruler, and that's much more convenient than actually having to place the ladder on the wall and trying to reach high to measure this length. However, even more conveniently for us, the value of this ratio has a name, and you can actually use a calculator to figure out that ratio. So I'm going to introduce the exact definition later, but this ratio b to a is called sine of 70 degrees, and if you punch this into the calculator, you get the value of 0.9397. Okay, so it actually has more decimal places, but we will just use the 4 digits, 0.9397. Okay, so if I use that value, 0.9397, and multiply by 12, I get 11.27. And if I multiply 8 times 0.9397, then we get 7.5176. Okay, what we get from this calculation is that the lesson that we learn from this simple example is that the ratios of a right triangle is pretty useful. And that's where this trigonometric functions come in. Okay. So, let's say you have a right triangle. If you have a right triangle, then you can talk about ratios of these sides. And in order to effectively talk about the ratios of the sides, we need to have good names for the sides. Now, the easiest side of a right triangle to identify and name is called the hypotenuse. This is the longest side of a right triangle, which is opposite of the 90-degree angle. And then the other two are called legs. These are called legs of a right triangle. And they are not distinguished initially, but however, suppose you pick one of the angles. The moment you pick one of the angles, then the two legs immediately obtain names. Well, first of all, this leg, that is the leg opposite of this angle. So naturally, the name for this leg is the opposite. I'm going to write OPP for that. And this other leg is right next to angle theta, so we call this leg adjacent. Okay. Once we have a good name for each of these sides, by the way, this angle, the letter I'm using to denote this angle is called theta. Theta. And it's a very customary letter. It's a Greek letter. It's customary to use theta for angles. So that's why I'm using this theta. Okay, so when you have picked an angle theta of a right triangle, then you can talk about sine theta, cosine theta, and tangent theta. Okay, what are these? Well, first, sine theta is defined as opposite over hypotenuse. Cosine theta is defined as adjacent over hypotenuse. And tangent is defined as opposite over adjacent. Since these definitions, although it makes sense, it's hard to remember which is which, people usually use the following acronym. They write SOHCAHTOA. Okay. If you've never heard of this terminology, you should try to repeat this, recite this many times, 100 times if you need, so that you don't forget this. Think of this as like a Harry Potter spell, so that it has some kind of powers. In fact, this has a very tremendous mathematical power, because if you remember SOHCAHTOA, 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 if you can recite this spell, then you easily remember these three important formulas, which will be used again and again. Okay, so sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Okay, along with these three functions, let's try to use this in a more specific context, so you can see how this SOHCAHTOA will be used. All right, here's the formula written again. SOHCAHTOA. Right. So let's try to apply this to a triangle whose base length is 1, and it has a very special angle, so that this angle is 30 degrees and this angle is 60 degrees. And this is 90 degrees, of course. Okay, suppose you're given such a triangle. Then what you can do is you can make a copy of this right triangle and flip it over the height and come up with this other triangle, which is also 60 degrees, and here's 30 degrees, then in this picture you immediately see that there's a lot of symmetry going on here, because 30 plus 30 is 60 degrees. All the vertices, all the angles, interior angles, have 60 degrees. What does that mean? It means that this triangle that you get by putting the two right triangles together is an equilateral triangle. An equilateral triangle has same sides all around. Now, of course, because this side is 1, this side should also be 1, and therefore the hypotenuse of this original right triangle will be 2. Okay, so now let's go back and draw this right triangle again. We just figured out that if you have 60 degrees here and 30 degrees here, and base length is 1 and the hypotenuse is 2, then well, if this happens, then we know that the hypotenuse is 2. That's what we figured out. Okay, now because we need opposite, adjacent, and hypotenuse, we need to know all the lengths. Let's try to figure out the height of this triangle. Let's call the height as A. Now, you have a right triangle with two known sides. How do you know the third? You apply something called the Pythagorean theorem. What is the Pythagorean theorem? It's a squared plus b squared is equal to c squared, where c is the hypotenuse. So if you apply it here, 2 squared, and since a is here, a squared, and then the other leg is 1, so you have 1 squared. Okay, so a squared plus 1 is equal to 4, which means a squared is 3, so you get a equals to square root of 3. Okay, usually when you take the square away, you should be putting plus or minus square root of 3, but for us, a is the length of a side of a triangle, so you should only put the plus. Okay, so now we have a nice triangle to work with. What is this triangle? Well, you have one side here with radical 3, another side which is the hypotenuse here, which is 2, and this side is 1. That is the angle 60 and 30 degrees triangle. Okay, let's try to figure out 60 degrees first. What is sine of 60 degrees according to this picture? Well, since we picked the 60 degrees, the opposite is square root of 3, right? And the hypotenuse is 2, and because sine is opposite or hypotenuse, we have square root of 3 divided by 2. So that's sine 60 degrees. How about cosine 60 degrees? Cosine 60 degrees is adjacent over hypotenuse, so adjacent, which is 1, divided by hypotenuse, which is 2. And then tangent of 60 degrees is opposite over adjacent, so it's opposite, which is radical 3, divided by adjacent, which is 1, so you have the square root of 3 as the tangent 60 degrees. Okay. Now remember that the opposite angle was 30 degrees, right? So this time let's use the same triangle, but then try to use this angle 30 degrees to figure out sine, cosine, and tangent. So it's still the same length, 2, 1, and square root of 3. Okay, sine first. Sine 30 degrees. Now what is the opposite of this 30 degrees? It's 1. So it's 1 divided by the hypotenuse, which is 2, because sine is opposite of hypotenuse. How about cosine 30 degrees? Cosine 30 degrees is you have adjacent, which is square root of 3, divided by hypotenuse. So it's square root of 3 over 2. And then finally, tangent of 30 degrees is opposite of 30 degrees, which is 1, divided by adjacent, which is square root of 3, because that's the definition of the tangent, right? So it's 1 over square root of 3. However, whenever you have a square root under the denominator, you should always try to make the denominator into an integer number. How do you do that? Well, you multiply top and bottom by the denominator. So you can multiply top and bottom by square root of 3. And remember, the value of a fraction doesn't change if you multiply the same thing top and bottom, because square root of 3 over square root of 3 is just 1. So effectively, when you multiply or equal 3 top and bottom, that's like multiplying by 1. So the value, the actual value doesn't change. And you get square root of 3 on the top, and the bottom, because this is square root of 3 times square root of 3, which is square root of 3 squared. So this much here is square root of 3 squared. And because squares and square roots cancel each other, you end up with 3 in the denominator. So you have the tangent of 30 degrees as square root of 3 over 3. Now, why is this important? Well, there are other reasons, but I guess for practical purposes, the most important reason is that sometimes these values pop up as choices in a multiple choice question, and if you computed your tangent in this form, and the multiple choice has everything as rationalized denominators, you call this process rationalizing the denominator. So if all the choices are given in these forms, then you wouldn't know that these two are equal. So one way to figure out whether two numbers are equal or not is to rationalize the denominator. If you always rationalize the denominator, then it's easy to figure out which two numbers are same or different. That's why you really want to rationalize the denominator whenever possible. Okay, so these examples probably gave you a better idea of how to calculate sine theta and cosine theta and tangent theta. Now, you might think we were lucky because we ended up with an equilateral triangle, which helped us to figure out the lengths. And that is true. In fact, this triangle that we just did was one of the few triangles where we can figure out the exact value of sine and cosine. So if you wanted to figure out, say, sine of 70 degrees, like in the example that we did in the beginning, you can't use plane geometry to do this, and you actually need the help of a calculator or a table. Before handheld calculators were invented, people used tables of sine and cosine values, and using those values they could figure out the ratios of lengths of a right triangle. Another question that you might have is that why do we use this base length as 1? What would happen if we started with 2? Well, if we start with 2 or 3 or something, let's say we start with 2, then all the sizes of the other lengths will be doubled. So if this side was 2, then this will be 4, and you get 2 radical 3. This is because any right triangle with the same angle here will be like triangles. They will be similar triangles. And when you have similar triangles, then their ratios would be the same. So in other words, when you're trying to find out sine, cosine, and tangent, it doesn't matter which size triangle you use. You can use a very big triangle or a small triangle, as long as you have the shape correctly matching, the value of sine, cosine, and tangent will not change. So that's why having this base length as 1 didn't really change our answer. So using a different size triangle with the same angles will give you the exact same value of sine, cosine, tangent. So these values are very well defined. Okay, let me show you another very well-known triangle. In fact, this is the only other triangle where you can use geometry to figure out the value of sine, cosine, tangent easily. And that triangle is the isosceles right triangle. Okay, so if you had an isosceles right triangle, so this length is 1 and that length is 1, then you can again figure out the other remaining side by using the Pythagorean theorem, which says 1 squared plus 1 squared. Square sum of the legs is equal to the square of the hypotenuse. 1 squared is 1, 1 squared is 1, 1 plus 1 is 2, so 2 is equal to a squared, and a becomes square root of 2. So that gives you an isosceles right triangle of 1, 1, and square root of 2. Now let's think about the angle of this side. Well, because this is an isosceles triangle, and we know that when you have an isosceles triangle, the opposite of the same sides are the same. So these two sides must be the same. And because if I call this angle x, then this should also be x, and we know that x plus 90 degrees, all the interior angles of a triangle, and therefore it's 180 degrees. So we know that x plus 90 degrees should equal to 180, and the only way that this could be solved is when you have x equal to 45. 45 plus 45 plus 90 gives you 180. So we know that this is a triangle whose angles here and there are 45 degrees. So they're both 45 degrees. Okay, now let's pick this angle as 45 and again try to figure out the sine, cosine, and tangent from this. First, sine of 45 degrees. Sine is opposite over hypotenuse. So its opposite is 1, hypotenuse is square root of 2. Now, this is another case where you have square root in the denominator, therefore you need to rationalize the denominator. How do you do that? Again, multiply the denominator's value, square root of 2, top and bottom, and use the fact that when you multiply anything to itself, it's that thing squared. 1 times square root of 2 is square root of 2, and square and square roots cancel each other, and therefore you have square root of 2 over 2. So that's the value of sine 45 degrees. Now let's think about cosine 45 degrees. Cosine 45 degrees is adjacent over hypotenuse. Adjacent to this angle is 1. Hypotenuse is square root of 2. And therefore this is again square root of 2 over 2. I'm skipping the rationalizing the denominators part because I already did it here. So both sine 45 degrees and cosine 45 degrees gives you square root of 2 over 2. And finally, tangent of 45 degrees gives you opposite, which is 1, and adjacent, which is 1, so you get the value of 1. Okay, from these examples that we just did, we can make the following table. If you're given degrees of 30 degrees, 45 degrees, and 60 degrees, the sine of 30 degrees is 1/2, cosine 30 is square root of 3 over 2, tangent of 30 is square root of 3 over 3, and so on and so on. So this table is the value of the trig functions where you can find the exact values of sine, cosine, and tangent from special triangles. These angles, 30 degrees, 45 degrees, 60 degrees, are called special angles. Now, for the future, you should memorize these values. However, you can do that later, because I will make a separate video to introduce to you an easy way to remember these values. Okay, that's all for the introduction.